So what we said last time is three things as far as properties of probability. We said that the probability of a certain event is 1. If something's going to happen, then it has a probability of 1. Probability of us having class today is 1. The probability of an impossible event is 0. If it's not going to happen, it has a probability of 0. The probability of me giving you $1 million today is 0. I couldn't give you $1 million if I wanted to, at least of my money. And then the other thing that we said is that the probability of anything else is somewhere in between. So if it's impossible, it has a probability of 0. If it's certain, it has a probability of 1. If it's anything else, it's somewhere in between 0 and 1. So the probability of any event is between 0 and 1. And I made a point of saying sometimes I get answers on a test, like what's the probability of blah, blah, blah. And sometimes I'll get answers like -0.5 or 1.7. And it's impossible for those things to be probabilities. Probability has to be 0, 1, or somewhere in between. So the two other things that we want to talk about today in section 11.2 are how to use complements to help us find probabilities, and also how to find probabilities of OR events. And both of these things are going to be related to what we talked about as far as complements and OR problems are concerned from chapter 10. So let's call this next part. Now I'm putting part B here because part A would have been, for this section, would have been what we talked about on the last part of class last time. So this is called the complements rule of probability. And you already know it, you just don't realize that you do. Let me illustrate that you know it. So Katie, I got a question here for you. It's supposed to rain today, right? Have you guys looked at the forecast? We're supposed to get like 4 or 5 inches of rain this week. So there's a chance of rain today. So Katie, if I told you that there was a 70% probability of rain today, what would you say would be the probability that it won't rain today? 30%. She just illustrated the complements rule of probability. Here's the deal. The complement of rain is not raining. Remember, the definition of a complement is everything else that can happen besides the event. Well, the only other thing that can happen besides rain is not raining. Well, when you state that in terms of probability, then, the probability of an event is equal to 1 minus the probability of the complement of the event, which we'll call E prime. Now, raining and not raining are complements. So I asked her the probability that it would not rain. And what she did was she took 1 minus the probability that it would rain. I told her there was a 70% chance of rain. If you change that to a decimal, 70% as a decimal would be 0.7. 0.70. So 1 minus 0.70 is 0.30. And she told me there was a 30% chance then that it wouldn't rain. That's an example of the complements rule of probability. In layman's terms, a good way to think about this is as follows. The probability of an event, think of that as your probability of E, probability of an event, is equal to what? 1 minus P of E prime, which means what? The probability that the event won't happen. Probability event does not happen. Now this is very similar to what we talked about with the complement rule for counting, which said the number of ways an event can occur is equal to the total number of possibilities minus the number of ways the event does not occur. Well, if you think in terms of total and probability, I said probability is either 0, 1, or somewhere in between. So the biggest a probability can be is 1. So this is following that same notion. It's 1 minus the probability that the event does not happen. And a lot of times it's far easier to think in terms of complements when figuring a probability than it is to try to figure the probability directly. Let me illustrate. Make sure everybody's done right. So let's illustrate by first taking a look at example 2, and then eventually we'll take a look at example 3. Well, example 2 is not really that much easier, but it does illustrate how a person could use the complements rule of probability. When a single card is drawn from a 52-card deck, what is the probability that it will not be a king? Well, it's not that hard to think about how many cards are not kings. There's 48 of them out of 52, so that's going to reduce to 12 out of 13. So we could think that way, and that isn't that tough. Or we could take 1 minus the complement of not king, and the complement of not king is king, obviously. So we could take 1 minus the probability of getting a king. Hey, Brandon and Katie, what's the probability of getting a king if you draw a card out of a 52-card deck? How many kings are there?
4.
4 out of how many cards?
52.
52, good. Hey, that was from the person who doesn't play cards. Nicely done. If you take 1 minus 4 out of 52, you'll get 48 out of 52. And if you reduce 48 out of 52, you're going to get 12 out of 13. Hey, Chris, convert 12 out of 13 to odds for me, please.
Which one stays the same? Is it 12?
Okay, good.
12 to 1.
Good. And Tristan, convert that to odds against.
1 to 12.
1 to 12. Okay, good. So, yeah, we could have used the complements rule on that problem, but honestly, it probably didn't save us that much work. On the next problem, it is going to save us a lot of work. So let's take a look at example 3. And we're going to change the problem a little bit on example 3. It says if 5 fair coins are tossed, find the probability of obtaining at least 2 heads. We're going to change the problem to say find the probability of getting at least one head. That's a little easier problem to start off with than find the probability of getting at least two heads. Well, in the last chapter, we discussed the following. We talked about how the complement of, and I'm going to put this in quotes, at least one is, now I pause here for a moment, let's think back through what we thought through then. So if I had 4 oranges sitting here on my table and somehow I could transmit them to Tristan, and I was going to pick to transmit to her anywhere from 0 to 4 of the oranges. The only way she wouldn't get at least one orange is if I transmitted to her 0 oranges. If she got 1, she'd get at least 1. If she got 2, that's at least 1. 3's at least 1, and 4's at least 1. The only way you're not going to get at least 1 of something is if you get 0. Now, what does that mean for us is in terms of probability? Here's what it means. Anytime you get an at least one problem, you want to think in terms of complements. The probability of at least one head will equal 1 minus the probability of getting 0 heads. So again, if it says the probability of at least one of something, this is the direction you're going to want to go. If we didn't, we'd have a lot bigger problem. We'd have to find the probability of getting 1 head. Then we'd have to find the probability of getting 2 heads, probability of getting 3 heads, and the probability of getting all 4 heads. So we'd actually have 4 different problems, and then we'd have to combine all those. Here, we're going to have one problem. We're going to have to find the probability of getting 0 heads and then take 1 from that. Okay, so let's do that. So we've changed our problem really to finding the probability of getting 0 heads. That still seems a little funky. So let's go back and do what we did earlier with Chris in the question he asked about. Let's go to the definition of probability. The definition of probability of 0 heads means this. It's the number of ways I can get 0 heads over the number of items in the sample space. So we're going to start with the sample space. So Tristan, if I toss 5 fair coins, is repetition allowed?
Yes.
Yes, it is. So therefore, we're going to have to fill in the number of ways each blank can occur. Tristan, how many ways can each of those blanks occur?
2 different ways.
Good. Nicely done. Good thinking. So every one of these can happen 2 ways. It can be heads or tails. And if you take 2 times 2 times 2 times 2 times 2, you're going to get 32. So 32 things can happen when you toss 5 coins. Now, this is for anyone. How many of those 32 things would include 0 heads? Katie, if I toss 5 coins, how can I get 0 heads? What has to happen?
You get
I get tails every time, don't I? They're all tails. So there's only one way I can get 0 heads, and that's if I get all tails. Okay, so there's 1 out of 32 probability of getting 0 heads whenever I toss 5 coins. So what's the probability then of getting at least 1 head? It would be 1 minus 1 out of 32. Which is obviously 31 out of 32. So the probability that you would get at least 1 head if you toss 5 fair coins is 31 out of 32. Now, if you're wondering about the original problem that's in your textbook, example 3, where it says, find the probability of getting at least 2 heads, okay? Well, the complement of at least 2 is 0 heads or 1 head. Well, the number of ways that I could get 1 head would be pretty easy to figure. It could happen any of the following ways. If I got a head in the first blank and a tail in all others, that's 1 head. If I got a head in the second blank and tails on all others, that's another way. Or the head could be in the third blank, the fourth blank, or the fifth blank, and everything else be tails. So there's another 5 ways to get at least 1 head. Combined with this 1 way to get 0 heads would give you 6 out of 32 ways to get at least 1 head. So the probability of getting at least, I said that wrong. It would be 6 out of 32 probability of getting 1 head or less. So the probability of getting at least 2 heads would be 1 minus those 6 out of 32, which would be 26 out of 32, or 13 out of 16. But that problem's a lot easier to see after you've done the at least 1 problem. It's a little harder to see otherwise. So if you get one of those at least 1 or at least 2 problems, I'm going to suggest that you go with the complements rule because it's going to make your problem a lot quicker. Okay, the last topic in this section is a big topic. It's called the general addition rule of probability. There's an I there. Here, it's better. The general addition rule of probability allows us to handle OR probabilities. Which makes me think a little bit about OR counting problems that we had. So here's the formula that we had in chapter 10 for OR counting problems. It said this, should look familiar to you. The number of ways events A or B can occur equals the number of ways that A can occur plus the number of ways B can occur minus the number of ways A and B can occur. So how does the probability formula work for OR problems? It's just exactly like this formula, except instead of looking at the number of ways it can occur, we look at the probability that it will occur. So the probability of event A or B equals the probability of A plus the probability of B minus the probability of A and B. So the two formulas are just alike, and they're just alike because they're closely related if you stop and think about it. Well, to illustrate the use of this formula, let's go to some card problems and take a look at example 5. And I'm looking at the bottom of page 592 here, in case you're wondering. It says if a single card is drawn from a 52 card deck, what is the probability it will be a spade or a red card? So if it's an OR problem, just like in chapter 10, we're going to use the OR formula. Okay, the probability of spade or red equals the probability of spade plus the probability of red minus the probability of both spade and red. Now listen, if it's an OR problem, just jump. My suggestion is always just jump to this formula. Remember what I said at the beginning of chapter 10. If you try to feel your way through this stuff, you end up getting tripped up. So just stick with the formulas. Recognize what kind of problem you have, go to the formula. That's what I'd say. Okay. Chris, Katie, or Tristan, if I draw a card from a standard 52 card deck, what's the probability it would be a spade? 13 is not a probability. Probabilities have to be 0, 1, or somewhere in between. Do you mean 13 out of 52?
Yeah.
Ah, I see. Okay.
1/4.
Yes. I'm going to leave it 13 out of 52, but it's not wrong to change it to a fourth. The reason I'm going to leave it 13 out of 52 is because I'm going to have built-in common denominators here in a second. If I reduce it, I may not. So, Tristan or Katie, what's the probability that the card will be red?
26 out of 52.
26 out of 52. Minus anyone, what's the probability the card would be both spade and red?
0.
0. Remember I said last time in the last chapter that if you got a 0 for that part, then the events were called disjoint or mutually exclusive. So 13 out of 52 plus 26 out of 52 is 39 out of 52, which reduces to 3/4. If we change the problem to say what are the odds of picking a spade or a red, you'd say 3 to 1. If we change the problem to say what are the odds against, you would say 1 to 3. Okay, now let's compare that to example 7 is what I have here next, which is another card problem. Find the probability that a single card drawn from a standard 52 card deck will be a diamond or a face card. So I'm going to call that probability of D or F. Now why don't you guys go ahead and flesh out how that formula is going to look on your paper real quick, and then I'll catch up to you. So we would set up this OR formula in the following fashion. Probability of diamond plus probability of face card minus the probability of diamond and face card. There are 13 diamonds out of 52 cards, plus there are 12 face cards, the jack, queen, and king, in each of the 4 suits. So 3 times 4 is 12. Minus, and the Jack, Queen, and King of diamonds are all both diamond and face cards. So there's 3 of those out of 52. That's the part right back here that a lot of students forget. They forget to subtract off the part at the end. So make sure you do that. 13 and 12 is 25, minus 3 is 22 out of 52, which would reduce to 11 out of 26. Now sometimes they may ask you for the odds of that event. So of course if they were asking for odds here, the top number stays 11. Subtract to get the bottom number. 26 minus 11 is 15. So the odds of drawing a diamond or face card is 11 to 15. The odds of against would be 15 to 11. Okay, Tristan, Katie, and Chris, do we have any questions? Was that a no? Okay.
Yeah, it was a no.
Okay. Here is what we're looking at for 11.2. 4 through 14, 16 through 20, 39 through 41.